Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique!
When I was an undergraduate, I took a course in pre-Socratic Greek philosophy. It was really fun. It began with the poet Hesiod and Greek myths. And the professor said something that really stuck with me during one of her lectures. She said that there were goatherds back in the day with nothing to do. So they talked to the gods because the gods loved listening to stories. And the Greek gods, my professor explained, were a lot like people. And just like people, their favorite story was the ones that explained where they came from. So the goatherds would tell them their own stories, how it began, their family trees, and how the present setup of the earth came to be. That gods, just like people, are obsessed with where they came from. It stuck with me because it had never occurred to me before that people might be obsessed with hearing their own stories. But it seems to be a universal thing to hear our own stories, to hear where our parents came from and how they met, and to hear how our grandparents met and made our parents, and back through history. Our stories don't just include our own family line, though. They go back to the gods and the creation of the earth and the creation of the universe itself. The word for these explanations is cosmology. And every religion I've ever heard has a cosmology, an explanation for the actors and the acts that built the world around us, as well as an explanation of how it all will end. So it's both surprising and obvious that science should endeavor to find similar explanations. It's obvious because we are human and our favorite stories are the ones that tell us where we came from. But it's surprising because how the universe came to be and how it will end are questions of a scope far beyond the evidence we can gather along shorelines and walking through forests and in laboratories. And yet we have. In so many ways, in so many fields, we're filling in the blanks of the story of our own cosmology. And the clues to answer the biggest questions seem subtle at first and come from humble origins, like studying show pigeon breeds eventually becomes an explanation for what and where humans came from on the earth. Or an explanation of how life can exist in our universe and how it can stop might originate with studying engineering water pumps in coal mines or the temperatures in brewing beer. In fact, from the study of thermodynamics comes the field of statistical mechanics and the concept of entropy. And then the idea that the complexity and structure in our universe might slowly be winding down, like a pocket watch run with a giant spring that can never be wound up again. Today on the Titanium Physicist podcast, we're going to talk about the heat death of the universe. And so speaking of the end of our universe, our guest today knows as much as anybody does because he's an author and translator of note. He's responsible for bringing Liu Cixin's world-shaking novels The Three-Body Problem and Death's End to the English language. But he's a notable author in his own right. His 2011 story, The Paper Menagerie, was the first ever work of fiction to win the Nebula Award and the Hugo Award and the World Fantasy Award, and it made me cry. I'm halfway through his 2015 silk punk epic fantasy series, Grace of Kings, which is just the first of the Dandelion Dynasty series, and it's the reason I can't sleep at night these days. He's written more recently a sci-fi story in the MIT Tech Reviews anthology called 12 Tomorrows. Welcome to the show, Ken Liu.
Hi, thanks for having me.
Oh, this is going to be so much fun. Now, Ken, today's show is going to be magnificent because of the physicists I brought together for you today. Arise, Katie Mack.
Ta-da!
Dr. Mack got her PhD from Princeton and did postdocs at Cambridge and Melbourne University, and she's currently an assistant professor in membership of the Leadership in Public Science Cluster at NC State. Now arise, Robert McNees. Dr. McNees got his PhD from University of Texas at Austin. He did a postdoc at Michigan and Brown and the Perimeter Institute, and he's currently a professor at Loyola University Chicago, where he studies relativity and quantum gravity. All right, everybody, let's talk about heat death. Hey, Ken, have you ever heard of the heat death of the universe?
I think so. I've heard the term.
All right. Well, do you want to start, Katie? Because you wrote a book about it?
I haven't finished writing a book about it, but I have finished the heat death chapter. So I'm writing a book about different ways for the universe to end, and the heat death is a really interesting one, partially because it's the most likely based on our current understanding of the universe and where it's going and how it's evolving. And so the heat death is an end state of the universe where basically the universe doesn't go away, it just stops being able to have anything interesting happen in it ever again, basically. It's a sort of end state of the universe that is destruction in the sense of everything we think of as being part of the universe, as being an interesting thing, is finished.
It's the boringest of all apocalypses.
Yeah, it is sad because, it's just kind of a fade out of structure, of order, of useful things. It's a fade out of life and intelligence, if that exists in the universe. And it's just like everything just kind of ends in this like darkness that's almost at absolute zero temperature and just persists forever, as far as we can tell, in this totally useless, finished, burned out state.
Instead of ending in ice and fire, our universe ends in like an interminable waiting room.
Yeah.
The sad deflated balloon of possible endings to the universe.
There are some like little caveats that I guess we might get to later where you can have kind of temporary reprieves in certain localized regions. But basically, as far as we can tell, the universe that we live in is evolving toward a state where it is completely uniform and boring and cold and utterly lifeless and without structure.
I guess that's my first question here. So in the heat death state, there literally will be no structure whatsoever. So no brown dwarfs, no nothing. Yeah. Just everything is just uniform, no atoms even.
Yeah, everything decays. And I guess we'll go through how that all happens. But we think that probably every kind of elementary particle and certainly every kind of composite particle is unstable if you leave it alone long enough, and it will decay. And so basically everything will decay into radiation after a sufficiently long time, and then that radiation will just be spread out by the expansion of the universe such that you have a very uniform, extremely cold state where it has a theoretical temperature, but it's almost absolute zero.
Yeah, so small that it almost doesn't mean anything different than zero. Mm-hmm. You just have this very scarce population of like maybe there are leptons left that can't decay or something like that. Really light leptons and photons, but nothing else really. So
how we get there is an important thing. It's not just that physicists are like, man, wouldn't it be great if there was nothing left?
Wouldn't it be great if the universe was just done?
Yeah.
This particular circumstance comes about from arguments from thermodynamics. So the heat death of the universe as a possible ending for our universe is something that we've been thinking about since the 1800s. Thermodynamics was kind of the study of engines and temperature. We wanted to know how heat moved around. I mean, it's in the name, heat death. Mm-hmm. So the way to think about this is like, one of the first concepts that we get in thermodynamics is the conservation of energy. So the total energy in your closed system, let's say you have an engine in your engine room and it's got a bunch of coal next to it. The total energy of that system is constant. Sometimes it's in potential energy, like in the coal, and sometimes it's in like useful working energy, like when you're pump is running and turning and things are moving. And so thermodynamics was concerned with how one energy turns into another type of energy. But the overall idea is the total amount of energy in your system is going to be a constant, right?
Yep.
Early engineers sorted energy kind of into two piles. You can think of it as useful energy and useless energy. So useful energy is the class of energy that you can use to do something useful, like pump water out of a mine or drive a locomotive forward. And then useless energy was energy that you can't do anything with. So like thermal energy is usually kind of a useless energy. So like the ambient temperature of the air in your room, we can't harness that energy to do anything useful.
Well, and this is something that's kind of intuitive. Like if you have some kind of machine or whatever and it's heating up, that heat where you're just heating the machine up, like if it's more inefficient, then there'll be more heat in the machine and you can't use that energy. Kind of like with a traditional incandescent light bulb, it produces light, but it also produces a lot of heat. And that heat is not useful for what you're trying to do with it. And so a lot of times like friction or like some kind of inefficiency in a machine will distribute some of the energy as heat, and that's like a less efficient machine if you're losing a lot of energy by heat.
So when the energy turns into heat, you can't do anything anymore with it in your box. So the idea here is a room in a box. Once you've burnt all your coal and you turned all that coal energy into heat energy, it's not coming back. You can't turn it back into coal energy to run your machine again.
Is it ever possible to reverse the process and turn the energy that's being dissipated into heat back into a usable form by applying more energy somehow?
I mean, not without making more heat somewhere else.
It can't be perfectly efficient.
Yeah.
You always come out with a little less.
Yeah. So like a steam engine, you're heating up water and then that's expanding and that's driving a piston and stuff. And so in some sense, you're using the heat from the burning of the coal, but it's also creating more heat as it all escapes. And so in the total system, there is more heat in the end.
This waste heat in a specific system, it goes by the name of entropy. You've heard the word entropy before, right?
Yep.
And the second law of thermodynamics says that in a closed system, the entropy, or this waste heat, is always going to increase. So the amount of usable energy in any closed system is only going to decrease over time. Because over time, no matter how careful you are, because there's no such thing as a perfectly efficient way to change one energy into another, any process you use, any type of motor you use is always going to make heat, and that heat's always going to be useless. So it just piles up until all of the energy in the box is going to be heat, and you can't do anything useful.
Can we talk a little bit about entropy a bit more? Because entropy, I've heard generally defined as a measure of the system's disorder.
Right.
But it's kind of hard to get a sense of it because the very words order and disorder seem to me somewhat subjective. But obviously in science, we have to have an actual definition for what disorder means that is not subjective. I mean, for example, if you drop a little bit of chocolate syrup into milk, initially, when the chocolate syrup is just a dollop swirling around in the milk, that looks to me like disorder. And when you've actually stirred it all up and it's uniform, I would say that's actually more orderly. But obviously, it's actually the reverse, right? I mean, the completely mixed up state is actually more entropic, right? So how do we get a better intuition of what entropy actually means?
So I think one of the things there that kind of interferes with how you think about it is that there's the notion of order and disorder, and there's also the notion of complexity, right? Mm-hmm. And they're not necessarily the same thing. So something can be disordered, but it can have a very low level of complexity. Like I would say that the description of the chocolate syrup and the milk, once it's all stirred in, I only need one rule to describe it once it's stirred in. In any volume, there's X amount. So
we talk about
complexity is very low.
Yeah, so we talk about it in terms of like the number of possible states, kind of. There are only a few ways for the chocolate syrup to be making a particular shape in the milk. Like there's you'd have to describe the path of all of those little particles of chocolate, and you'd have to describe this very complex path, and there's a lot of different things you have to specify. But there's only kind of one way for the chocolate to be all around in that shape. But once it's mixed in, you can swap individual chocolate particles all over the place, and it really doesn't make a difference to the total, like what it really looks like. And so, as Bob said, you only need like one sort of parameter to describe that. But there are so many different ways for it to happen because switching the particles around in lots and lots of different places in the milk is totally fine. You get the same answer. Does that make sense?
Yeah, I get the complexity versus the not complex distinction. Mm-hmm. It's still not totally clear. I guess maybe entropy is sort of a measure of a kind of set of many different states that are not meaningfully distinguished from each other.
That's a really good way of putting it. So, for instance, if you take that glass of milk and you dissolve the chocolate syrup in it, then you could characterize what you would call the macro state of the milk by saying, like, okay, it's a kind of pleasing light brown color. And that's basically all you need to tell me for me to know that the syrup has been dissolved in the milk, right? But there are many, many, many what you would call microstates, like actual configurations of here's this molecule of chocolate syrup and here's this molecule. And there are lots of different ones that would all correspond to essentially the same macro description. It's this pleasing brown color.
Okay.
So there are so many more states consistent with this pleasing light brown color than there were for the way it was organized previously, which is essentially just this kind of dollop as it falls into the milk. And so in that sense, there are lots more states. And so that's the notion of kind of order and disorder that we're talking about.
Okay. I think the reason why I think it might be hard for someone who has not, gone through the math rigorously to understand it is that the idea of entropy here is we're saying there's a bunch of many possible states here not meaningfully distinguished from each other. And the meaningful part here is an empirical objective measure, meaning the system can be in any of the billion different states, but empirically we don't see these differences as mattering in any sense. Whereas when there's less entropy in the system, the different states are empirically different. That is, they manifest their differences in some physical way that we can measure. Is that one way to think about it?
Well, sort of. I mean, one way I might think of it is, let's say that you take this glass of chocolate milk and you make a sort of three-dimensional grid. And for in each cell, you say whether it has a chocolate particle or not, or like what particle is there,
Yeah.
And in the state where you've just dropped the chocolate in and it hasn't mixed in fully, then for the cells that have that chocolate in it, you have like a large number of particles in that cells, and for the other ones, you have none. But then for the fully mixed state, all of the cells kind of look the same. So if you swap them around, it doesn't make any difference. Whereas with the more ordered state, with the chocolate making this particular path, if you swap a whole bunch of those cells around, it will look totally different. So it's kind of a matter of how evenly populated this sort of space is versus not.
That makes sense to me intuitively. But if you zoom in, into a very, 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 very tiny part of the milk, you would see actually quite a bit of differences, right? Because each moment there may be a section with 2 chocolate particles, and then the next second there will be only 1, and the second after there's 3, or something like that. Like, if you set your scale small enough, wouldn't you see a whole bunch of very random local variations?
Yeah, right. Yeah, which is really important, because when we define the entropy, we're defining a large system, and it matters whether that's a closed system or an open one. So how you measure the entropy in a closed system is very different from how you measure the entropy in a smaller part of a system or an open system.
Okay.
Yeah, I think you're talking about actually distinguishing the different what we called microstates a second ago. And, if you can do that, if you can resolve the states, then there's really no ambiguity about what's going on. If you can zoom in and say this molecule is here and this molecule is here, then you know everything that's going on. But when you step back and you only make these macro observations, when the entropy is really big, that's essentially saying like, wow, there could be, any one of a number of things going on consistent with what I'm seeing, which kind of connects with the idea that very disordered. Whereas when you zoom in and can say something specific, then it's not as essential a concept.
Okay, gotcha.
Let's take a step back here and put things in context.
Yeah.
So the idea here is when we think about thermodynamics, we're kind of conflating 2 different kind of historical theories. There was the original classical thermodynamics, it's often called. People didn't know what atoms were or that atoms existed. They knew what fluids were. And so they were pretty sure all they could do is measure the macroscopic properties of a system. And so there was this idea that there was kind of 2 types of energy, useful energy or useless heat, entropy energy. And nobody kind of knew why they behaved that way, but we developed fairly sophisticated arguments about how to analyze your evolving system. So if you take your material in a box, you take an ice cube and a hot cup of coffee and a lump of coal and a whole bunch of oxygen and a lit match, and you put them all in a box and close the door, eventually, as the system evolves on its own, the entropy is going to increase in the box, the useful energy is going to decrease until eventually the entropy in your box will reach a maximum. And so that essentially was what the argument system, we had no idea what entropy was, we had a vague idea of what energy was, but this is the series of arguments that led us to the idea of heat death, which is to say the universe as a whole is kind of a closed system. You can't get stuff from outside the universe, and so over time, the useful energy in the universe, say all the coal underground, because you're like an English engineer, so all the coal, all I care about is coal and maybe charcoal. The amount of coal in the universe is finite. You burn all the coal, goodbye. There's no more useful energy in the universe. Eventually, we're going to run out, and our steam locomotives won't be able to run anymore. And that's kind of the framework that we use to talk about heat death, is that you say, well, there's more than coal in terms of energy. There's light from the sun that can make trees. And you're like, yeah, but eventually the sun's going to go out, so the total amount of energy is always, or the total amount of useless energy is always going to increase. Okay, so that's classical thermodynamics, and the deal was in the turn of the 1900s, just before then, theories of atoms started to emerge describing what matter was. And what that allowed physicists to do at the time is develop a new theory called statistical mechanics, which said, hey, what if everything's made out of these little atoms and they're just jiggling and wiggling around? But, if you've got a cup of hot water, you can't track where each and every atom or molecule in it is, but you can talk about statistically where they should be. You're like, each individual atom of water is just bouncing around at random inside of this cup of water, but statistically, we can describe where it might be. And in describing statistically what the matter is doing, the different compositions of matter, you end up with a description of the universe that explains all of the laws we came to in thermodynamics. So your picture that you were asking us questions about is a statistical mechanical picture of entropy. All we had was this idea that for who knows why reason, the useless energy always increases in a system until you reach some maximum and then you can't do any more work. The statistical mechanics picture was really cool because, it said things like, the kinetic energy of vibrations of atoms is what heat is. So temperature is. So thermal vibrations, little atoms bouncing around, that's what heat is. It also came up with a really interesting explanation of what entropy was. It introduced entropy as, like we've been saying, statistical ensembles. This is a bonkers concept, and let's walk through what we've talked about. The idea here is you've got a glass of milk. Where's the milk atoms going to be? They can be anywhere inside the glass of milk. They're just going to bounce around at random. And then you introduce a dollop of chocolate syrup. At first, all the chocolate syrup is in a lump. It's like a microstate. We know where all the chocolate syrup is in there. But you think about it, over time, diffusion happens, right? Over time, the atoms bump into each other and knock each other about, and they get more and more spread out over time. And so after a long, long, long time, each molecule of chocolate could be anywhere inside the glass. And so statistically speaking, the chocolate will be described as being diffused through the glass of milk. It could be anywhere, which generates your picture of a completely mixed up glass of milk. But the interesting bit here is that we do actually have a method for talking about how the entropy changes. We have a method for describing entropy as a number in terms of this disorder.
Okay.
Yeah.
Let's hear it.
Well, it's kind of complicated. You have to take the logarithm. But essentially what we're talking about is all you know about the system are kind of like macroscopic descriptors. All the chocolate's over here, all the milk is over in this region. You don't know where each individual molecule of chocolate is in the overall lump of chocolate, but you know kind of that all the chocolate is over here. And so you enumerate, you count up all the different possible ways you can get the same picture. And you go, oh, well, there's 700 billion different ways we could rearrange the atoms of chocolate when they're in this big lump But if they're all in this lump, there's only 700,000 different ways, whatever, right? You just put the
right,
number
because
together.
there's a smaller space for them to
That's
be
right.
sent.
And then you say, after a long time after diffusion has happened, those chocolate atoms could be anywhere. How many different ways could I arrange these chocolate atoms into, oh God, I'm just going to stick with it. These chocolate atoms inside the milk to get this, overall diffuse picture. And there's 100 kabillion of them. There's just so many more because it occupies so much larger space.
That's really helpful. Okay, go on.
Yeah. So statistically speaking, you're like, well, at the start of it, I know that the chocolate can be in one of 100 billion different microstate, the state of all the atoms at one particular time. I don't know which one it is, but I know it's one of these 100,000, some number. And then you say after diffusion has happened and the chocolate has bounced around and is now occupying the whole cup, there's 100 kajillion different possible ways. And so the probability that it's going to be one particular state of this is 1 in 100 kajillion, right? It's a much bigger number. And so the idea here is that over time, as your milk, like you mentioned, the microstates in the milk are always evolving. If you look at any little droplet of milk in there, sometimes there's going to be 1 atom of chocolate, sometimes there's going to be 4 atoms of chocolate, right? It'll change over time. But then statistically speaking, the probability that all of those atoms of chocolate are going to go from all mixed up down back into the corner is there's a probability associated with it, but it's exceedingly, exceedingly small.
Okay.
And so the numerical descriptors of entropy, which is how much usable energy there's in the system, stops being one of an energy accounting game and starts, interestingly enough, becoming a game of statistics. What's the probability compared to of all of the atoms of chocolate being in this one place compared to the probability that they're everywhere? It's much smaller, so chances are your system won't evolve to one where it has a low entropy compared to one where it has a high entropy. The entropy corresponds to that probability that your particular atoms are going to be in a particular configuration.
So let me ask a follow-up question that I think will clarify this. So let's take 2 situations. One situation is you have the totally mixed up milk with chocolate, and it's close to the freezing point of water. So all of the molecules are moving a little bit, not very vigorously. The other one is where the milk is heated near the boiling point so that every atom is jumping around up and down. The second state has more total heat energy in it. But if I'm understanding this correctly, the 2 systems actually have the same entropy measure. Is that right?
No, I mean, entropy also is connected to heat. So when the particles are moving around faster, there is higher entropy. Kind of because they can be in lots of different places more quickly, I guess you can think of it that way.
Yeah,
whereas,
that's the part I was confused by, because statistically speaking, right, the 2 states seem to have the same number of states and the same probability. But your point is, if they're moving faster, it actually makes the probability even less.
Yeah, if all we wanted to keep track of was how many, in Ben's words, chocolate atoms there are, in a little volume, then that would seem disconnected. But there's really kind of no way to ignore the other thing that's going on, which is, as Katie says, it's heating up, things are zipping around faster. And then the statistical description of what's going on and how the state evolves, you have to keep track of all that stuff.
Okay, so, good. That makes sense.
Did we cover open and close?
Well, so it is important whether the system is open or closed, because in a closed system, you know how the entropy is going to evolve. In an open system, sort of the heat energy can go somewhere else, and so you can't keep track of it in the same way.
Yeah, I think the important thing is, in a closed system, we expect the entropy to increase. Yeah. And then in an open system, because you can move things around, send something to some, thing you're connected to, that you can have entropy go down, and there's no.
Well, I guess open refers to the fact that you can put energy into the system and take energy out.
That's right. It's in contact with something that you can kind of exchange with.
Yeah.
For instance, imagine instead of chocolate milk, we were talking about salt. You add salt to water. In terms of entropy, we would say you can't get that salt back out of the water, but you can. You can boil away the water, evaporate the water, and the salt will all accumulate back in crystals at the bottom, right?
Right. It's just that you can't wait around until the salt spontaneously becomes a crystal, because that doesn't happen.
Yeah. So in the second example where you're boiling it off, you're essentially in an open system. You're giving the system energy, and you're letting the water molecules leave, and through that process, you can return the salt to a low entropy state.
Yeah, I mean, and it's sort of about when you're actually keeping track of stuff versus when you're not. If you let particles leave and you don't keep track of exactly where they're going and what they're doing, then it's an open system. Or if you let energy come in that you weren't keeping track of before, then it's an open system.
Yeah. But here's a point that may be a little bit of pushing it, but the probability that the salt will spontaneously crystallize is very low, but it is not zero, right? I mean, if you had a glass of water with salt and it's sitting there for the age of the universe and beyond, at some point there's a probability that the salt will spontaneously crystallize.
That's right. Yeah. So if it was a closed system, like if you really weren't letting any energy come in or out, and you just had the salt dissolved in the water, then there is a chance that the salt just kind of spontaneously turns into some well-organized salt crystals sitting on the bottom. But you look at the entropy associated with that macro state and the entropy associated with salt dissolved in the water, and the difference is enormous. And it's something, there's a factor that tells you how likely it is to get the less likely thing. And it has to do with taking that difference in the entropies and doing the number e to that power, and it's a huge number, and that kind of suppresses it. That tells you how unlikely it is. And because that's such a huge number, you wait, however many lifetimes of the universe, and you aren't very likely to ever see it happen. In principle, it could, but it's just not very likely.
Right.
And that's a fascinating concept, right? Because in classical thermodynamics, it's not going to happen. The entropy is always going to stay high. But if you introduce kind of statistical mechanics as an underlying explanation for thermodynamics, you can start to say, well, it could happen. It's just really, 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 really improbable.
Well, actually, that sort of thing is catnip for science fiction writers because, with the heat death of the universe, right, as you were talking about, I mean, I could envision that if you just let the universe sit in that completely entropic state, but if you wait long enough, it might spontaneously get back to the Big Bang, right? And then we can start over again.
This isn't just science fiction. This is actual research in cosmology as well. So once you allow quantum mechanical fluctuations into the picture, you can do lots of things. And people do talk about a possibility of the heat death creating a new Big Bang or our Big Bang coming from a fluctuation of a heat death universe. I think we were going to talk about that a little later as we get more into the topic.
We'll get there. We'll get there.
Yeah.
It's a pertinent thing to mention because all we've talked about so far is, well, pretty much statistical mechanics and thermodynamics and entropy. So applying it to the universe is a fascinating thing because if you think about the argument is over time, you start out with an aquarium and it's sealed and covered in styrofoam or whatever. It's a closed system. You take an ice cube, you throw it in, you take a glass of hot water, you throw it in. Eventually, everything's going to end up the same temperature and you'll get uniform distribution of molecules and it's very boring, right?
Yep.
Okay. We want to apply this to the Big Bang. The argument is like, okay, so the end of our universe is going to be the state where all of the coal is now just random carbon atoms and everything goes away and you don't get any interesting structure anymore because the increasing ratchet of entropy has dissolved all of the interesting parts of the universe and everything's really boring and the same everywhere. When we look at our universe, our information from the Big Bang comes from us starting a large-scale structure of the universe and the cosmic microwave background. But when we look at the cosmic microwave background, which is a record of the temperature of all the different parts of the sky, the idea is, long time ago when the universe was much hotter than it was, you had all these atoms floating around, bumping into each other, creating heat. There was a temperature, they were generating photons, and then it cooled to the point where all these photons just kind of got left alone. And so when we map the cosmic microwave background, we're mapping those photons from the early hot universe. But the photons I'm mapping come from different parts of the sky. They're like 14 billion-ish years old. The photons I get from looking to the North Pole and the photons I get looking at the South Pole come from entirely different parts of the universe. One is 14 billion light years up, and the other one comes from 14 billion light years down. So they come from completely different parts of the sky. But when you do that, the temperature of all these parts of the universe is pretty much the same, which tells you something weird. It tells you that the early universe was kind of a uniform soup where everything was the same temperature and everything was made up of pretty much the same stuff. Shouldn't that be a really high entropy state?
Yeah. That sounds like it.
So why in our universe do we start out with a hot soup and
that's not intuitive,
right?
You would expect something completely different. A highly ordered state at the beginning, right? That's what you would expect.
Yeah.
Again, the ordered versus simple kind of sneaks in, right? Because we say we would expect something highly ordered, but in fact, it was really simple. You don't need much to describe what it was like. So in that sense, it is highly ordered.
I want to get some intuition of this. It was highly ordered but simple. How is that different from the chocolate milk example where it's highly disordered but also simple? Like, what is the difference between these two?
I mean, it comes down to the fact that gravity is a factor, and gravity interacts with entropy in really strange ways. So this is not an easy thing to explain because this is something that's not sort of well quantified within physics. But basically, so the early universe was a very dense state, but a very uniform state. And it had little tiny fluctuations of density. And over time, those fluctuations of density collapsed and became, galaxies and clusters of galaxies and so on as the universe expanded. And for reasons that are very complicated, a gravitationally collapsed system, like a black hole, is higher entropy than the equivalent mass of just like gas in a cloud. So when you bring things together by gravity, that actually sort of increases the entropy in some sense. So a sort of smooth, uniform universe with a lot of mass, but not a lot of sort of fluctuations is like a lower entropy state than a universe with a whole bunch of galaxies and stuff in it. And then as you go on, over time, you get into a situation where you go through a state where there's a whole lot of black holes and things, and then those decay and the particles decay, and then you get to a highest entropy state. So
yeah, that is really unintuitive to me. I mean,
yeah,
because that feels to me like the key to understanding this.
One way to think about this isn't in terms of the temperature distribution of one type of particle. It's also, you have to include the possibility that you can change into different genuses material in the universe. So early in the universe, there were atoms. Lots and lots and lots of atoms, right? That was very interesting. But you can have other types of stuff out there. You can have photons. You can have weird, heavier particles. So let's just imagine like a cloud of gas in space. So a cloud of gas in space in the middle of nowhere. It's pretty uniform. Just imagine this is just a big spherical boring cloud of gas. The temperature everywhere is about the same. It's just made up of hydrogen atoms floating around in straight lines, occasionally bumping into each other. Okay? We know that that's going to gravitationally collapse because gravity. So it collapses down to a thing going from a big cloud to a ball, a planet in space. It's reversible, right? I mean, you could take a whole bunch of dynamite, you could blow it up and turn it back into a cloud of gas, right?
Okay.
But why in our universe does the collapse go one way? And the answer has to do with photons. The gas collapses. As it collapses, the temperature of the gas increases, right? There's thermal radiation. Those hot photons, they get radiated out into space. One way to talk about it is this collapsing ball of gas isn't in a closed system, it's in an open system, and it's turning things into photons. You're changing the number and different types of particles in there. You got a whole bunch of new photons as it collapses and heats up, and those photons stay photons. They go out into space.
Right.
And then the system doesn't have enough energy to go back to being a cloud. Another way to talk about this, though, is as a closed system. Just imagine you've surrounded your ball of collapsing gas with a great big thermos with styrofoam balls and mirrors and stuff like that, right?
Okay.
It collapses down. We go from a system that's made entirely of atoms to a system that's made of a mix of atoms and photons. The entropy increase means that it can't go back from the material being a mix of types to being all of one type.
Is that in some sense because the photons represent useless energy in the classical term? So
that's kind of one way to think about it. But you can think of it in terms of statistical mechanics too. It's just like, how many different ways can my energy represent itself? At the very start, it has to only be a particle. That particle can be anywhere inside the box, high entropy, right? But we know what type of particle it can be. As it collapses, turns to thermal radiation, now it can be one of a whole bunch of different, it could be a hot photon, it could be a cold photon, it could be a photon.
Okay, got it. So your state space has become bigger.
Yes.
You're also creating like space-time curvature too. So like the gravity is warping the space, and so the sort of shape of space is no longer a kind of smooth, flat space. Now you have this kind of dent in space from the gravity, and you can kind of think of that as another way of encoding what's happening.
I think I get it. But I guess my question then is, why wouldn't the heat death of the universe be similar in that you have lots of local gravitational structures and matter being all sorts of different states? Wouldn't that be a bigger total state space than everything being uniform and smooth?
There's one more factor that we kind of left out with this discussion of the Big Bang. We start, in this kind of very hot state, and it seems kind of counterintuitive. So imagine we took our glass of chocolate milk, and we got it pretty hot enough that, like, normally if it was uncovered, it would boil out, but we keep it in a small volume. Right, so it's got an entropy, and its entropy is higher than it would be if it was cold. But now imagine kind of letting it take up a bigger space, even maybe evaporating and being this chocolate milk gas that fills up the room. Its temperature goes down, but the volume it has access to has gone up dramatically. And so the number of states accessible to the system, microstates that kind of correspond to the same macrostate of this fairly dilute chocolate milk gas, is so much bigger that the entropy has still gone up. So even though the original state of the system, seems, it's hot, very hot, it seems like it should be high entropy, this other thing that's happening, that is kind of the growth of the universe, of the volume, means that there's lots more states that the system has access to.
Okay, yep, I get that.
Earlier, to answer your question, earlier I was talking about how, you get genuses of particles, and as the number of genuses of particles can increase, you can get an increase in entropy in your system, even though it corresponds to the matter all collecting in at a point, right? So if you think about it, stars, for example, they don't just turn stuff into photons, they can take your hydrogen atoms and combine them into heavier different types of atoms.
Right.
So the stars, the reason they can be hot and radiate heat out into space is because they're essentially great big entropy engines. The entropy in the system is always increasing as the stellar furnace combines different atoms. The more material you pile onto the system, the more entropy it's going to have, because the more different types of things you can make in your stellar furnace. If you follow this argument, the solar system would have more entropy if all of the planets in it, instead of orbiting the sun, ended up inside the sun.
True.
Arguably, the heavier your object is, the more concentrated all the material is at the center of it, the higher entropy the overall system is able to evolve into. But in terms of classical celestial mechanics, there were just two planets orbiting each other. Their orbits wouldn't decay. But in Einstein's general relativity, there's another type of particle you can kind of generate. You can generate gravitational waves. You can think about gravitational waves as another genus of thing that the energy can go into. Okay. And so over time, if you have two things orbiting each other, some of the energy in the system is going to turn into gravitational waves, and it's not going to turn back.
Right, it just dissipates.
Right? Yeah, it just goes out into the universe, right?
Yeah.
So, in modern physics, lots of the energy sustaining the Earth's orbit around the sun is eventually going to turn into gravitational waves, and then the Earth is going to end up in the sun, and then the sun's going to have a higher entropy.
Yep.
And so one of the arguments is that over a large scale of time, everything in the galaxy is going to end up in the center. The entropy is going to increase as some of the energy turns into gravitational waves. That's not going to come back, and everything's going to collapse down. And that's why heat death isn't a whole bunch of different, orbiting, black holes orbiting the center of the galaxy. It's everything in one glob.
But then what happens to black holes is important too to this picture.
Right.
So I want to say just a brief thing about Hawking radiation. So you've heard of Hawking radiation or black hole evaporation? Yeah, so Hawking radiation is this idea, it's due to Hawking, and a couple other people worked on it. And the idea is that if you leave a black hole alone and nothing's happening to it, it'll slowly kind of evaporate. It'll produce high energy particles and photons that'll kind of come off of the black hole. It'll kind of glow with a low level of radiation, and over time that will carry away mass, and the black hole will shrink, and it will evaporate completely. It'll eventually kind of blow up. And so that's a way to convert a black hole into a whole bunch of particles and radiation, and this is called Hawking radiation. And kind of the way that this came about was this sort of thought experiment where, okay, you have the second law of thermodynamics that says that the entropy has to be increasing over time in any system, right? And you also have this fact that if you have a black hole, if you throw something into the black hole, the black hole is going to get a little bigger. And so there's this kind of idea that the area of a black hole or the mass of a black hole can't go down. That's always going up. But,
Right.
Okay, this is going to be a complicated analogy, but I need to have a system that takes entropy out of and sort of puts it somewhere else. Okay, so one of the things that people talk about for entropy is you can't unscramble an egg. Okay, so right, like you scramble an egg, that's increasing the entropy of that little egg, and you can't put it back together. But let's say that you had a machine that very, very carefully took every particle of that egg and aligned it perfectly and eventually created your egg again. You know, so
Your
it's
3D printed egg. Yeah, sure.
yeah,
Okay.
yeah. So you have this egg unscrambler, but of course, because of the second law of thermodynamics, like that will increase the total entropy of like the room in which this is happening. It'll heat it up, basically. So let's say that you create this egg unscrambler in this box, right? And you unscramble your egg, and then you snatch the egg away, and then you throw the whole room into a black hole. Then you had a scrambled egg, you reduced the entropy in that egg, and then you hid all of that extra entropy behind the horizon of this black hole. And so now you seem to have violated the second law of thermodynamics. You've reduced the entropy in something, and you've hidden the extra heat waste energy, the extra entropy behind the horizon of a black hole.
I
From
see.
the universe.
Okay.
Right? So that's a contradiction.
Right. Okay.
Yeah,
Right.
it goes back to John Wheeler. He posed this thought experiment. In physics, when something is hot, we think of it as radiating. If something has a temperature, then it radiates. Classically, black holes are perfectly cold because they don't radiate anything, right? They just swallow things and that's it. And so he imagined this scenario Katie described, which is, you take something with entropy, something hot, and you toss it in there, and now it's in this perfectly cold thing. Where's all the entropy gone?
Right.
Yeah.
You've somehow magically reduced the entropy in the universe just by
Right.
shuffling all that mess into the black hole, which
Right.
is, kind of nice, but doesn't work.
Yeah. So that's not allowed. And so that was the idea that led to the idea that black holes have to have some radiation, because there has to be some way for that entropy of what you threw in there to come back out again. And in addition to that, whatever the entropy of the black hole is, it has to be kind of the maximum entropy you can have for any object of that mass, because otherwise you might have something that's like way hot or something that has a really high entropy, you throw it in the black hole and that reduces, right? So a radiating black hole has to be the kind of maximum entropy state of any sort of collection of that mass. So what you get from that is that anytime you have a collection of matter, it strictly increases in entropy when you put it into a black hole. And as that black hole is evaporating, that strictly increases the entropy of the universe. And so that way you can have this path through to higher and higher entropy all the time.
Yeah, it's sort of like conservation of increasing entropy. You don't have somehow disappearing entropy magically. Okay, yep.
That's right. It's maintaining the second law of thermodynamics, which is that the entropy always has to be increasing.
The evolution of the universe is one in which, first you have sort of gravitationally collapsing objects, and then those will increase in entropy by turning into black holes, and then those black holes will evaporate, and other things that maybe are not in the black holes will sort of decay. And so you're evolving toward this state where the universe is full of this sort of disordered radiation, either from the decay of particles directly or the evaporation of black holes. So can we go through like just the chronology of the heat death real quick?
Stages.
Okay, so we start with some kind of Big Bang, and we're not going into the details of what that is or how that happened. But you start with this extremely low entropy state, relatively, of a pretty uniform but extremely dense universe that is in some sense smaller than the universe we are in today. And over time, that universe is expanding, and within that universe, those little fluctuations in density are collapsing on themselves and creating structure, the stars and galaxies and things like that. And those structures have higher entropy than a bland, uniform-ish distribution of very dense matter. And the universe is expanding, and so there's more and more space, and these objects are getting farther and farther and evolving, and you're using up the gas and creating stars, and the stars are burning out and polluting the universe with heavier elements, and then you get people and stuff. And then over time the stars will burn out. And because things in the universe are getting farther and farther apart, because the universe is expanding, and in fact is expanding in an increasing way, so it's accelerating in its expansion due to something we call dark energy. It's expanding increasingly. Things are getting farther and farther apart from each other. And so the kinds of processes that happen to create new stars, like clumps of gas running into each other and heating up and stuff like that, that happens less and less often because galaxies are not colliding with each other anymore. And so each galaxy, the stars within it are kind of burning out. Everything's kind of fading away. And as the stars are burning out and as things are evolving with, gravity and gravitational radiation and all of that, you're getting a universe that's in each little patch of the universe where there's some matter. That matter is evolving more into black holes or kind of decaying in some way. And so each part of the universe that has some matter is getting more and more isolated from every other part because the dark energy is increasing the expansion so much that things are carried away so far that they can't be observed anymore and they don't interact anymore. And so each part of the universe becomes a little isolated island of this sort of decaying matter and black holes. And then those black holes are evaporating over time. And so each part of the universe is becoming more just this very empty part of the universe where it's got a little low-level radiation that's diluting over time as the universe it continues expanding. And so eventually you have a space where it's just this very, very low level of radiation that's been diluted. And it hits a temperature floor. So there's a lowest temperature that you get to at the maximum entropy state. And that has to do with the fact that this state of space-time that you get to toward the end has a kind of entropy associated with it. It has a cosmic horizon, and that horizon has an entropy associated with it in a sort of similar way that a black hole has a horizon associated with it, and there's an entropy associated with that horizon. But in any case, that leads to a kind of minimum temperature at the maximum entropy state. And that's a space called de Sitter space, where it's really just expanding universe with almost no anything and almost no radiation in it. And that sort of just persists forever in this sort of useless state where there's only disordered energy, just waste heat, and nothing else. And nothing can ever happen again because there is no structure and you've reached the maximum entropy state and you can't do anything with that.
But it continues to expand, even in that state?
Yeah, it keeps expanding, but in a sense that kind of is meaningless because there's no marker on the expansion anymore.
There's no one to observe the expansion. There's no variation in what's there where you could see some change caused by the expansion. So it's uniform. It's dark and uniform and lonely, and that's it. And the temperature Katie's talking about is phenomenally low. Like if you take kind of our best cosmological measurements right now and use that to pin down kind of the dark energy driving this expansion, the temperature that comes out for this kind of long-term future is on the order of like 10 to the minus 30 Kelvin.
Or maybe even 10 to the minus 40 or something like that.
It's so low that it almost seems meaningless.
Wow.
Yeah.
So what's left in the universe at that point? I mean, what is this? What kind of radiation or anything is left?
Extremely long wavelength radiation, the occasional lonely lepton that hasn't decayed.
Yeah, but it's basically extremely cold radiation, and that's it.
Wow.
Hooray!
The funny thing is, it actually looks a little bit like the beginning of the universe, only, it's uniform. It's just...
Yeah, like we were saying before, so at the beginning of the universe, we think it's comparatively low entropy, but also complexity level is very simple. And then kind of all of existence as we know it and life and all the interesting stuff is this detour into high complexity as the entropy gets bigger. But then eventually it ends up back in this state where the entropy is very high, but the complexity is low again. So you don't need much to describe that final state.
Yeah, I mean, one way I think about it, I mean, I'm sure this is not right, but it's kind of how I like to think about it, which is at the beginning, when there are no possibilities really. I mean, that one state is all you can be. The entropy is very, very low because there are no possibilities of being other particles, of being other things, of bigger space to do things in. And then you go through the stage where there's lots of possibilities and entropy goes up because there's just so many more things to do. And at the very end, you still have this huge space of this state space of potential, but you have nothing left at that point. It's a high entropic state. The possibilities have all been expanded and there's all the stuff out there, but you actually don't have any of those possibilities. I mean, you just have this one dead, cold thing. It's kind of like a metaphor for life.
It might be worth saying something about life, because people do sometimes talk about life as a violation of the second law of thermodynamics. It's not, but they talk about it that way because life is a kind of process that reduces the entropy of a particular life form, right? So it's a process of creating order, right? A life form is more ordered than a pile of chemicals, but because it's these are not closed systems, the entropy does go up in building a life form because a life form produces its own heat and it produces waste products and all of this kind of thing. So the entropy will still be increasing all the time, even when life is happening. But one of the other ways in which this is a relevant issue is that one thing you do need for life is you need an energy gradient. So you need to be able to move energy from one place to another. So this is something that comes up a lot in talking about extraterrestrial life. You need like a sun to produce energy that goes from the sun to the planet, or you need like a hydrothermal vent to take energy from the bottom of the ocean up, so you have to have some kind of energy difference in order to have, something that can create life, that can build something, that some energy you can work with. There has to be a gradient. It can't be uniform all around you. And this is the same problem you run into with heat death, is that there's energy, but it's so uniform. There's no gradients, and so you can't do anything with it.
It's worth mentioning that, we're talking about kind of the heat death of everything and the really, really far future. And we're talking about timescales that are like really colossal, timescales that make astronomical timescales look like nothing, right? But it's kind of worth pointing out that in most of the universe, as it is right now, heat death has kind of already happened. Most of the universe is empty and just has cold CMB photons in it, cosmic microwave background. And that's radiation that, is like 2.7 Kelvin. And that's pretty cold. And so there's not much that can be done with that, right? For something to do something useful with that, it would have to, be cooled down below that, so that it can kind of mine some energy from it. And that's kind of the overwhelming volume of the universe as it exists today, right? So we always talk about the heat death as something in the future, but kind of in a practical sense, in a lot of places, it's already pretty close to heat death, right? And we're just kind of this rare phenomenon on these little corners of the universe where interesting things are still happening.
Yeah. And as you go on, that's just more and more true because the universe is expanding, increasing the distances between interesting places. And you can define an observable universe as sort of radius of the horizon, And if you count up all of the sections of observable universe, then most of those are pretty empty and will just increasingly become so.
Yeah, that's depressing.
It's a very bleak future and also kind of a bleak present. For kind of the only thing here that can make you feel better is at least you're in one of the parts of the universe where interesting things are still happening.
Yeah.
True.
Katie, did you want to mention Boltzmann brains?
Oh gosh, we've totally glossed over Boltzmann brains. All right, so the heat death state, the maximum entropy state of the universe, you have this totally uniform universe with no useful energy, nothing happening. But as always, things get much more interesting when you factor in quantum mechanics. And so one of the things you have to think about is that quantum mechanics says, spontaneous weird stuff happens in the universe. And if you're just sitting around in this maximum entropy universe forever, once in a while, something weird is going to happen. And that weird thing that's going to happen is that you get a fluctuation of part of your universe into a lower entropy state. And that lower entropy state can then do stuff, can have processes happening, can have stuff evolving or whatever. And you can have these sort of spontaneous rearrangements of this tiny amount of radiation or the sort of energy of the vacuum even into objects, into like matter. And so people have talked about this, as we sort of alluded to before, as a way of restarting a universe or starting a universe. Is you have this heat death state, and you have a little fluctuation of part of that space into a Big Bang, into sort of
the smaller
beginning
one,
state.
sort of.
Yeah,
sure.
Yeah, the beginning state of the universe, and then that sort of expands and evolves, and it sort of evolves back into this maximum entropy state, and sort of rejoins this soup of nothingness, right? So people talked about that, like, okay, maybe we can have a fluctuation into the Big Bang, and then that's a great way of starting up the universe. But then other people were like, well, okay, if it's possible to fluctuate into a Big Bang state, it's even more likely to have just a much smaller fluctuation where you create just one galaxy. But then it's actually even more likely to just create one planet.
Sure.
And in fact, it's even more likely that instead of creating a whole planet full of people who are observing the universe, you just create a single brain, like a person, like the brain of one person, and that person just happens to have the memory of the whole universe and imagines that they have observed the cosmic microwave background. That state is actually much less complicated. Like, you have to do less to create a brain that thinks that the universe exists than to create the universe itself. So this is called the Boltzmann brain problem, which is a generic problem you get with any universe that you're trying to create out of quantum fluctuations from a heat death state, is that in some ways of calculating, you're more likely to just produce a brain that thinks it's a universe that came out of a heat death state, and in fact will immediately spontaneously decay back into the sort of quantum soup.
So we could theoretically be figments of such a brain.
Yeah, now you could be that.
Yeah, Ken, what we're trying to tell you is that none of this was here a second ago.
Yeah.
We were in heat death, and there was a spontaneous fluctuation that produced your brain and all your memories, which didn't exist a second ago.
Yeah,
that is pretty cool. And I assume it will flutter out of existence as soon as we stop recording.
It could, or it might just wind down. You'll never know.
Yeah, it's hard to say. Like, there are different ways of measuring what it takes to do that fluctuation. And so there are ways of measuring where it's more likely to produce a Big Bang than to produce a brain. There's a sort of complicated accounting because this is a sort of very weird state. But there are a lot of fun things you can do with this possibility of fluctuations. Like, for example, you get Poincare recurrence. This is a really cool topic. I really enjoy talking about this because it goes back to some kind of really bizarre sort of philosophical thought experiments. There was a book that Nietzsche wrote. And in this book, he brings up the idea of eternal return. And eternal return is this idea that what if every moment of your life you live over and over again an infinite number of times? And like, wouldn't you just be like screaming in agony if this were the case, right? And this sort of dystopian thought experiment of this, you repeat your life over and over again. But in a sort of quantum mechanical system, like a heat death universe, any state that the universe could have been in the past, any state that's possible or that did happen, can happen through fluctuations, and in fact will happen an infinite number of times. So like a universe that is arranged exactly as the universe is exactly at this moment, because it's possible in a heat death universe, you will in principle fluctuate randomly to this moment again and again and again forever, just at a long sort of time scale. So like the time scale between those fluctuations will happen. And so this is called a Poincare recurrence. So in some sense, Nietzsche's idea is plausible in this cosmological sense that every moment of the universe repeats infinitely many times over and over again with just long times in between in a heat death universe, which is a really fun thought, I think.
Yeah, that is. Let me ask a follow-up question on this. So if it's possible, however unlikely, that in a heat death universe, we can spontaneously have a recurrence of a galaxy or this whole moment or even a brain, why isn't that a violation of the second law of thermodynamics? Why? Because spontaneously we did, in fact, decrease the entropy of the system.
Didn't you say it yourself that, like, when you were talking about a glass of chocolate milk, there was some finite but very, very, very small probability that all the chocolate milk particles...
So I'm trying to understand, why wouldn't that be considered a violation if that can spontaneously happen?
Because you're dealing with infinite amounts of time.
And quantum mechanics, which sort of messes with this whole picture and usually only matters on a microscopic scale, but in this case could matter on a much larger scale. So that makes everything more difficult to align with this idea.
Yeah, the second law, is essentially, as Ben was saying earlier, a statistical statement that you're overwhelmingly likely to increase the entropy. But there are timescales associated with that. You're always overwhelmingly likely to increase the entropy on timescales short enough that these other phenomena don't happen. The odds of a fluctuation that take you back a low entropy state, are suppressed by huge numbers. You can estimate the rate of that, and then based on that, you can figure out roughly how long it would take. And on timescales much shorter than that, you're always overwhelmingly likely to increase the entropy. But once you stretch things out into this very, very long, dark, bleak future, you kind of move beyond that, and there's always the possibility of a fluctuation causing something extremely unlikely. Although some physicists will argue that, in fact, this final state of the universe is different and our intuition about these fluctuations are wrong and we shouldn't expect that, and it just is bleak and ends and that's it.
And, discussions about this continue in the literature and among cosmologists. It's a fun topic, and it's definitely not one that is all tied up in a bow. We're still trying to figure out exactly what to do about the low entropy state of the early universe and the high entropy state of late universe and how that all fits together. As far as we know, the second law of thermodynamics is super solid for every kind of system that we ever really deal with, and for anything where we're not looking at the quantum mechanical fluctuations at the very, very smallest scales. But quantum mechanical fluctuations will affect macro scales if you have an infinite amount of time, and so then it gets a little bit fuzzier.
Yeah, I mean, this is just so interesting, because now you can even imagine some crank saying that, well, perpetual motion machines are actually very possible. All you have to do is give it infinite time scale and wait for the fluctuations to come, right? I mean, the system will reset. So there you go.
Yeah, pretty much. Well, that was great. Thank you, Katie. Thank you, Bob. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Dr. Katie Mack, you get the lowest entropy fruit, an apple.
Nom, 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 nom.
And Dr. Bob McNees, you get the highest entropy fruit. It's a raspberry.
This is good.
I'd like to thank my guest, Ken Liu. A list of the different novels of his and short stories will be on the website for you to link and buy and read. They're absolutely fantastic. Thank you very much, Ken Liu, for coming on the show.
Thank you very much for having me.
All right. Hey everybody, it's time for announcements. That was a really good episode. By the way, I've read Ken Liu's books since we finished recording, and they are amazing. So, announcement time. 0th announcement. One of the reasons we've had so few episodes lately is that I've been moving cities and changing jobs. So there's this episode and the episode following this that I've recorded before the move. But then after that, I won't have any new content to release until who knows when, because we have to get set up. I'm thinking a month or two. Anyway, so first announcement, please give us an iTunes review as always, or tell other people about us online. Your iTunes review help other people find the show, and even if we're on kind of hiatus, we have a very deep back catalog. They could listen to an episode a week for a year and still have more to listen to. Second, I'd like you to follow us on Twitter at Titanium Physics. I do make announcements about what's going on that account once in a while. But also, sometimes we are in the lurch for a guest. Maybe we'll book a show and everything will line up and our guest will have to cancel at last minute. I'm going to start using Twitter to find a replacement guest. So if you're on Twitter, you might find yourself on the show. And finally, we're still humbly soliciting your donations. Your donations go to paying for server fees and our project to transcribe episodes as they come out. So if you'd like to donate, please follow the links on our website. Please give us a donation through Patreon, which allows me to take a payment every time I make an episode. But if I don't make an episode for 4 months, you don't have to pay for it. Or alternatively, if you want to make a one-time donation, there is a PayPal link. And this particular episode of The Titanium Physicist has been sponsored by a collection of generous people. I'd like to thank the generosity of Preston Huft and Christopher Sherman for their donations. I'd also like to thank all of our Patreon sponsors:
Daniel Lauzon, Patrick Yan, Asterios Kokonos, Kevin Forsyth, Yer Panay, Hoanim Duong, Stian Henriksen, a TPR Jones, Pascal, a man named Ryan R., and Michael Usher, Senor Canada, Adrian Schoening, Sarah Stradler, Louise Pantanila, a guy named Ben, a Mr. Matthew Lambert, a fella named Ayush Singh, a David Myrtle, a Mr. Ryan Foster, a Janico Freifenberg, Steve Smethurst, Magnus Christensen, Bart Gladys, and Mr. Stuart Pollock. Our Emperor, Courtney Brooke Davis, Mr. David Lindels, Mr. Carl Lockhart, and our eternal friend B.S. and Randy Dalzell, a Ms. Tina Rodeo, the enigmatic Ryan, a gentleman named Crux, and Gabe, Evan Weens, David D., Dan Vale, a Mr. Alex, WTL, Mr. Per Proden, Andrew Waddington, Mr. Jordan Young, and John Bleasy, a Brittany Crooks, James Crawford, Mr. Mark Simon, Tucson's Gang of One, Mr. Lawrence Lee, Sixton Linnison, Mr. Simon, Keegan Eade, Andreas from Knoxville, Cadby, Joe Campbell, Alexander Zani is great, Winna Brett, Eric Dutch, Etienne, and a gentleman named Peter Fan, Gareth Eason, Joe Piston, David Johnson, and Anthony Leon, as well as Doug B., Julia, Noah Robertson, Ian and Stu, Mr. Frank, Philip from Austria, and Noisy Mime, Mr. Shlomo Dalal, Melissa Burke, Yassine Uarazazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, Mr. Victor C., Ryan Kloss, Peter Clipsham, Mr. Robert Halpin, Elizabetha Teresa, and Paul Carr, Mr. Ryan Newell, Mr. Adam K., Thomas Shire, Mr. Jacob S., a gentleman named Brett Evans, a lady named Jill, a gentleman named Greg, thanks Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Ladlington, Kelly Wienersmith, Jocelyn Rita, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So that's it for Titanium Physicists this time. Remember, if you like listening to scientists talk about science in their own words, there are lots of other lovely shows on the Bracula Media Network. The intro to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Good day, my friends, and until next time, remember to keep science in your hearts.
I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hopped down Magnolia Boulevard.
We're lucky.
Yeah, seize the day, man, you know.
You should totally trademark that. That's good.
I do have a motivational poster I made about seizing the day that has to do with the sun is going to burn out in a few billion years, or it's going to engulf the Earth, or at least engulf Venus, and the Earth will fall in some way because of like dissipative forces, and so you should seize the day before it kills us all.
Talking about kind of the fate of life and how life needs energy gradients, one of my all-time favorite speculative physics papers is called Time Without End, written by Freeman J. Dyson, I think like the late 70s, like 1979 or something. And it was a response to this book that Steven Weinberg wrote called The First 3 Minutes. And in Weinberg's book, he was looking at the early universe and what happens. And Dyson said, well, what about the field of eschatology? Like, why doesn't that get any love? Let's talk about the end of the universe and how long we can stretch things out. And so, he talks about physics as it was understood at the time, like how far out can we forecast? What is the really long-term fate of the universe? And it's built on assumptions that we know now are probably not right. In particular, it was, before we suspected that there was dark energy. But it really sits almost at the intersection of physics and sci-fi because so many ideas, are there in the paper that kind of made their way into stories. But also he borrowed things from Fred Hoyle's Black Cloud because he examines how long you can stretch out life in a universe like that. As the universe gets colder and more dilute, what can you say about the physical principles that underlie life? And then how far can you push them and still call that thing life? It's a fantastic read. Even if you don't understand all the physics that goes into it, it's kind of one of the more fun speculative things you can read. And it's got a great timeline of all the things that happen in the far future, from things that we understand to things you might not ever expect. We have a pretty good idea of how the lowest mass stars work and how long they can burn for, and it's on 10 to 100 trillion years or something like that. And then we can estimate how long it takes for planets to be pulled away from their stars by close encounters with other stars, or for orbits to decay by gravitational radiation. But also, as things get really cold, quantum fluctuations, making matter lose its shape, or even kind of spontaneously, this kind of spontaneous long-term radioactivity of regular matter as quantum fluctuations turn it into other elements, and everything kind of turning into iron in the far, in 10 to the 1500 years or something like that. And, then everything collapsing into black holes and black holes evaporating and things like that. It's a tremendously fun read.
Yeah, I went through it
if you like bleak futures.